our session for AP Physics C, mechanics. We're going to be focusing on mechanics and a little splash of E&M on the side, but I'm really excited to be here with Gina Ruiz-Houston tonight. Tonight, we're going to help you do what we can to get ready for this exam. Remember, at Marco Learning, we're going to be going live in 18 tests and subjects throughout this week. We're already about halfway through. Gina Ruiz-Houston has been the star of the show on the Marco Learning YouTube channel over the last couple of years, guiding a lot of our Physics 1 reviews. But tonight, it's all about Physics C. And later this week, if you're looking for Physics 1 and 2, check out the recordings on our channel and check out the reviews we're going to be hosting later in the week. Mrs. Ruiz-Houston, I want to turn it over to you. I'm delighted to hang out in the chat with everyone else. What are we going to be learning tonight? And what do we have to look forward to as we get ready for the big exams tomorrow?
The big exams tomorrow, but I think you guys have got it. Now, one thing I'm going to say before I even really get started is please do not spend all night studying. Please just review one more time and go to bed. It's so important that you have a good rest for this because Physics C, actually any one of the physics, isn't that great? Any of the physics subjects that you take, all of them are thinking exams. It's not rote memorization. They're all new questions every year. They're fresh. They're made and designed just for you. And so the better you can think and process information, the better you're going to do on the test. So without further ado, let's please get started because we have a lot. So just a couple of facts and questions that I typically get at the beginning. Yes, of course, our exam is tomorrow in the afternoon. Depending on your school, you may be excused from the morning and just come in right before lunch. It depends. Just please make sure you have something to eat, you're ready to go. And it's not a terribly long exam this year. We're changing the exam for next year, so you're going to be the grandfather group coming in with the old exam. So lucky you. Now, remember, we have 50% multiple choice, 50% free response. Not that there's 50% number of questions, it's just how much we're crediting those sections for. Now, to kind of give you that multiple choice, and I know I'm talking fast, so I'm sorry. What are you looking at? You're looking at 35 questions in about 45 minutes, and that's going to be 50% of your score. Now, remember, on your multiple choice, you could have discrete questions, meaning you have some sort of question stem and a single answer that you're picking. But you could also have something where it's a group so that you have some sort of scenario and possibly 2, maybe 3 questions that go with that scenario. So pay attention as they're wording the question so you know what you're looking at. Oftentimes, your questions are going to have you interpret something. So there'll be perhaps a diagram, a graph, something of that nature, maybe a physical situation. College Board loves those. Okay, they love to give you graphs if you have noticed. And anytime they're giving you a graph or a diagram, you need to stop for a second and actually look at it. Don't pass it. It's not something that they're doing for no reason. Anytime they're printing it on an exam for us, for physics, doesn't matter which exam, it's important because they have to spend extra money to get that diagram on there and to get it sized right and drawn in the correct manner, particularly graphs. So please do take a moment and look at those. Oftentimes, you're going to be referring to somebody's information, looking at their hypothesis, thinking about what's going on, how should they test it, looking at that data in the graph, is that graph reasonable for what you're looking at, and trying to talk about the relationship between different quantities. Yes, there will be a couple straight plug and chug kind of questions where you're just calculating, and those are usually everybody's favorite because it's just a quick math question. And you will have to look at people's different opinions from time to time to support scientific claims. Really, the meat of that, though, happens on your free response. So you're only going to have 3 questions on your free response, and it's not going to be just A, B, and C sections. Oftentimes, it's like A through F sections. And realize if you do get, let's say, part A wrong, okay, but you come up with some sort of number. If you use that number in, say, part B and part C, we're not going to double penalize you. So if we can see what you wrote in A, and we notice that you're using that same thing in B and C, but you're using it properly, we will only lose points in part A and we'll give you the points in part B and C, etc. So when we're reading it, we actually stop and look at that, and we don't double penalize you at all. We all have our little calculators out there. Yes, we're kind of geeky like that. All of us little readers have our calculators, and we're going to check the work anyhow if you did use something inappropriate, okay? Now, one thing that's kind of critical to remember is on these 3 questions for our FRQ, one of them is going to be an experimental or a lab-based type of scenario. So it could be something where they're already giving you the data and you're the person who has to look at the data, perhaps graph it, perhaps transform that graph, discuss it, or perhaps you're creating some sort of experiment or justifying why the experiment is valid or invalid and how the person set it up. So realize one of those 3 is going to kind of be experimentally based, okay? Now, the others, as well as that experimental one, they are going to have you look at our basic science practices. So to think of what those science practices are, I kind of put them in bold here, and I'm sure your teacher has talked about them, but just to kind of run it through our brain one more time so we see what we're up against. One of the science practices is for you to interpret and describe visual representations. What does that mean? That means I might have a graph. I might have to look at the graph and say, what does that graph mean? Or what does the slope of that graph mean? Or what does the area under the curve of that graph mean? Or I might have some sort of scenario where they're showing me a lab experiment or a lab setup, and I have to know what kinds of things am I going to measure there? Or what kinds of information could I get out of that? Okay. When I'm doing the second one, question and method, it's how you come up with a hypothesis and how you design an experiment. Now, that particular one is a little bit harder on us as the graders or the readers, because you guys can come up with all kinds of different experiments that are valid. And so when it's that experimental question, we have more than one scenario that we're grading. So we don't have it that it's just one specific way. It's any materials that are in a typical physics laboratory. Okay. I can tell you my students much prefer to use a meter stick and their phone rather than a motion sensor, just because they're more comfortable with it. But maybe at your school, you have photo gates and motion sensors and this, that, and the other. It just depends upon what you're comfortable with. And so that's okay. The argumentation, you have to develop a claim. You have to support it with evidence. So what kinds of data would you like? What kinds of calculations would you create or solve to try to provide enough evidence to make your argument? That one's often a difficult one for students to do. The best suggestion I have there for an argument is look at that equation sheet, which I'll show you in a moment. I know you have it, but start with somebody on that equation sheet. And it tends to help focus your brain so you can kind of think through what I should say, okay? Analyzing data, as I mentioned. Coming up with a theoretical relationship. So in other words, what would an equation look like if you were asked to create the equation? And we're going to do one of those today. Solving just general problems with math. And that could be algebraically, and that could be with the calculus, okay? Some of the things lean themselves more towards the calculus, some lean themselves more towards the algebra. It's a matter of where you want to use which kind of math, okay? Use it where it helps you. Use it where it's not cumbersome, okay? And then the last one there, representing data and phenomena. You may be given data and have to graph it, okay? You may be given a graph and have to transform it. So realize that kind of material is also on the test. So not only are for the free response, you're going to get a experimental, but amongst all 3, you're going to hit all 7 of these science practices. That's the aim of the current free response questions. Okay? Now, if you notice, I'm going to go back just for a second. You have 45 minutes and 3 questions to work on. So wild guess, but here we're looking at about 15 minutes a question, of course. Now, is it possible to finish? Well, it is possible. On this one, there are students who do finish all 3 questions in their entirety. What if I get stuck, Miss Ruiz? It happens, okay? If you do get stuck, do the best that you can. In a sense, as I say for my kids in my class, steal as many points as you can here and there. And then hopefully that total is enough from the various pieces you have to push your grade up to a 3, 4, or 5. So you don't have to get every single question, every single point, but get as many points as you can, regardless of which section, okay? Now, here's, of course, your beautiful constant sheet. Bluntly, we're not going to use much other than this one, the acceleration on the Earth, and gravitational constant. That's really where we live. Most of these are really going to help me on the E&M test, but not so much with the mechanics. But it is a joint equation sheet. As far as our next one, that's our constants. Our equation sheet looks like this. I love it. Maybe you don't, but I love it. Part of why I love it is it does give me a good basis for any one of my experimental questions or any one of my free responses. It gives me somewhere to start. And usually when we're grading or reading, we like to see where you begin and you pick something from here, and then you're creating or deriving from there. The other thing that I really love about the equation sheet is that they have the important vocabulary right here. So when you are trying to describe something or you're coming up with the argument, it helps to give you those words to use, those physics key terms or concepts to use. And this is just published straight away on College Board's site, and you're going to see one in whatever color they tend to use this year. Yes, you'll have this equation and constant sheet for both sections of the test, free response and multiple choice. It didn't used to happen that way, so be glad you have it on both sections. And you can use your calculator, of course, on both sections at this point. Okay, so please make sure that you do so. The other page is going to be your traditional, just in case I forget because I'm nervous section, which is the general geometry and trig. And we do forget it from time to time, and the general calculus. The one that's most familiar, that's oftentimes forgotten, is the circumference of a circle. And you would think that that's ludicrous for you to forget, but it happens. And that was perhaps, I think it was about 2014, 2015. More than half of the people in the US forgot that one. Why? Just because they were nervous. They're taking a test. So it does happen. So when you get stuck, please definitely go back to the equation sheet and the constant sheet. There may be something there to kind of save you and push you along. Here's our breakdown, of course, of our mechanics. And I set it up this way specifically so you could kind of think it through. Look at kinematics, Newton's laws, and work and energy. You're looking at more than half the test there. And I would wager your teacher probably spent a good serious amount of time, probably through Christmas or so, just hitting those 3 sections. And now you're panicking, oh my goodness, I just lightly hit oscillations. I just lightly hit gravitation. But if you look at those are so tiny in comparison. I'm not saying avoid them, but at the same time, you probably have a good solid meat of most of the tests right there. As far as system of particles and momentum, it feeds so nicely into work and energy. You're really looking at that you know more than you think you do. So give yourself a break. It's going to be all right. Okay. I did the same kind of graph for E&M. And again, if you're doing 3 of the sections, most particularly, just say electric. That's it. Forget magnetism in its entirety. You've covered a good chunk of the exam, and you might get a 3. So realize you know more than you do, and to hang in there, and don't you dare give up. Keep on slugging away. Now, a couple of just pointers, hints for multiple choice, okay? The whole way we as writers of the test look at you as students is we are going to design it so that we're looking for your knowledge. It's not going to be one of those questions that, you flip the book and you go, oh, the answer's right there. It's not like that at all. We're looking to see what's in here. How do you process? What are the physics terms you know? How do these things work? So we're looking at and designing questions for your knowledge. Sometimes the terminology can get a little hefty, shall we say. So I would suggest if it is getting hefty for you, read the question twice. Read it more if you need to, okay? But you need to understand what it's asking specifically, not just quickly put down an answer. So you need to think about what they're actually asking. So read it, reread it, read it again if you need to. As I said, diagrams and graphs are critical. It costs College Board more money to print them and to make sure that they're right. So if they've bothered to do that, it's an important piece, okay? I like to suggest that you kind of sketch and label things on the side as you go. So once you've read it once, once you've read it that second time, you've already kind of got, in your way of thinking about it, your little notes on the side so that you can go ahead and proceed and answer the question. If possible, of course, eliminate questions or eliminate possible answer choices. If you've got to guess, go for it, okay? Please, there is no penalty for guessing anymore. There used to be. So if you don't know the answer, truly, I can't eliminate anything, I'm guessing my little rear end off, that's okay. Pick, let's say A. And everyone I don't know, I'm putting A on. Or whatever that favorite letter is, put that. But be consistent. So if you truly don't know, put that same letter each and every time, okay? And then once you're finished, just in case you need to double check, and if you have enough time, please do, just quickly reread the problem and make sure you solved for what they were actually asking for. Do pace yourself. Not every question is going to take the exact same amount of time. Some of them, they'll take double time. Some of them, you'll read it and go, oh, I know that one, and move on. And that's fine. Just don't go so fast that you maybe didn't really read it all the way through, okay? Answer again, every single question, no penalty for guessing. If you get stuck, that equation sheet is a godsend. Again, go back to it, look at it, see if you can grab something and move through. Now, at this point, I'm pretty sure your teachers have practiced with you, and you've done a gazillion tests and worksheets and practice problems all through the year. Anything of that nature, as you're sleeping tonight, dream of physics, okay? And you'll see all those in your head. And that's going to be that experience or information base that you're going to pull from. So we're not asking you to repeat something. We're asking you to think through the physics in your head and come up with answers. That's how we're making this test. If you're looking at multiple choice, you're about a minute-ish or so per question for you to get through. Free response. I'm even more reading carefully. Okay, I put exclamations on this one. One mistake I notice with my particular students is since there's part A and B and C and such, and sometimes College Board does I and double I and triple I and all of that, sometimes in that progression, College Board changes the scenario. So part A and B are about such and such scenario. And then by part C, maybe we added an extra mass, or we took around this, or maybe friction was added to the system. So you need to kind of make sure you don't get caught there. So you're not answering that next section based on the original scenario. You're answering it relative to the scenario that's currently being asked. So slow yourself down just a tad to make sure that you're reading carefully of what's going on. And I suggest that you pre-read all free response questions. And you might say, oh, Ms. Ruiz, why are you going to do that? That's wasting time. Not necessarily. Look through all three. Whichever one is just beautiful to you, that's the one I want you to start on. If that's number 3, you do number 3 first. Okay, if that's number 1, great, do that one first. The reason why I mention it is that one of the years in AP on, I can't remember what year it was, in Physics C, there was a question that was the first question, and everybody kind of got stuck there. And a number of students didn't even try number 2 or number 3. They just got stuck on number 1. And they should have looked at and used their time and spread it out. So please spread it out. Look at all 3. Which one can I answer the best and fastest? Do that one. And then do the next one. And then do the next one. Okay. So you get to pick. It doesn't matter which one you start with as long as the answers are there. Okay. Please try to write as legibly as possible. We, as graders or readers, we try really hard to read your answers and to understand. But if we truly cannot read it, we truly cannot grade it. So please make sure it's at least as clear as you can make it. I'm not saying that you have to erase, cross it off, rewrite it over here, and we're good to go, okay? And let's say I'm reading your paper, okay? Perhaps I am. If I'm reading your paper and I'm really having a hard time reading it, we can make it bigger. We can ask somebody else at the table, hey, can you tell me what you think that says? So we won't just automatically, forget it and give you a 0. We do try as best as we can to read it. But the more clear you are, the better we are able to grade it. Organize yourself. Organize your solutions. And please, 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 I know your teachers harp on this. I do too. Show all of your work. But I know the answer. Yeah, show your work. The way we grade is oftentimes we're trying to find pieces of your work to give you points for. So let's say you wrote down the equation, +1, okay? You start working out the equation, plus another 1. You get to the answer, or maybe you had to substitute something in, plus another point. So in other words, all these points for this free response, it's not just based on exclusively on your answer, it's going to be based on how you're getting there. So think like that we're going to be trying to give you points as you move through your work. So showing your work can only help you and only can increase your score. So please do it because I asked, do it because your teachers asked, but more importantly, do it because that's how you get all the points, okay? One biggie, and I know your teachers have harped on it, do not break your free body diagram apart into its components. College Board has been really delightful recently about writing that in the question itself. So whenever you're drawing a free body diagram, draw just the forces that are acting on that object. Now, if to figure it out, you need to over here draw another little sketch and do your components, great, but not on the actual dot that they give you, okay? And as I say here, answer every part of every problem every time. Even if you're not positive you're right, there probably is something in your physics brain that you're going to put on paper there that we probably can throw a point or two at. So please tell us everything that's in your head about this, and we could be able to give you a couple of points here and there, which of course increases your score. As far as units, students always ask, do I have to put my dimensions and units on every single thing? No, but please make sure it's in the final answer so that in case we're counting units, it's there. I can't say we give many points for units. We used to, but not recently, but every once in a while there is one there and you don't want to miss it when you get it. And on that same line, if they're asking you, if College Board's asking you to say derive something and put it in specific terms, like they want it to say tension as tension T, okay? Or maybe they want tension as F sub T, and they've specified it in the question, do it into whatever unit or constant or expression that they want, because that's what we're going to be grading as far as your final answer, okay? I know that's a lot really quick for you. So just to kind of cover the units. Now, I did do all 7 units and some little tidbits on each one. If I'm running long, okay, what I will do is I'll show the slide, pause for a second, show the next slide. The reason why I'm going to do that is that you are going to get this recording shortly, okay? And when you get the recording, then you can stop the tape at that and see those and review those. So I did all 7 units, kind of the major, for lack of better wording, important points to remember. Okay. Certain ones will go a little faster through that I think you have better, and other ones will take our time a little bit with. So unit 1, here we go. So position, displacement, velocity, and acceleration. Remember, position is just where am I located? And oftentimes we're measuring it relative to a point, to some 0, 0 that we pick. Now, is that 0, 0, say, always at the bottom of the cliff? You could. Or can I make the 0, 0 at the top of the cliff? I could. It depends upon which way you choose to solve the problem. So as long as you're noticing where that reference point is and you're communicating it, if it's a free response question, we're good to go. Remember, displacement is change in position, and it is a vector, whereas distance is not. That's a scalar. We've got our velocity is the rate of displacement, and velocity, remember, we've got our derivative there, okay? Acceleration is the rate of the velocity changing, and we've got our derivative there. Cool? Okay. I know I'm going fast. Now, most of the time, you're going to have a velocity time graph, but you could have a displacement time graph. If so, my slope's going to be velocity. If we have a velocity time graph, the reason why that one's everybody's favorite is the slope is acceleration, but that area under that curve is my displacement. And then, of course, our acceleration versus time graph, depending on how it's asked, most of the time I see it as either something circular or it's something where you're showing gravity and you're showing it below and you're showing it roughly at 9.8 or 10 if you prefer. Okay. Different wording here. Uniform motion versus uniform accelerated motion. Uniform motion means I have no acceleration. So I'm moving at a constant rate, no change in velocity. So I'm moving at 55 miles an hour or 55 meters per second, and I'm staying right at that number, okay? Uniform accelerated means I keep changing, I keep accelerating, but I'm accelerating at some constant. So like I'm accelerating at 9.8 meters per second squared or at 2 meters per second squared. So I'm going at a constant accelerated rate. If I had an accelerated rate, wouldn't my velocity be changing? Can you see the difference between the two? So one of them, the velocity is being maintained. The other one, the acceleration amount is being maintained. Now, speaking of amount, what is that? Amount is going to be magnitude. Every year we get a question where students say, I don't know what magnitude is. Magnitude just means the number, the amount, okay? You know this, all right? Cross product and dot product probably is on there just as something to use. It's not going to be its own separate entity. As far as the special projectile motion equations, you've done these before. You've plugged and chugged them before. I just look at them one more time before you go to sleep so that they're in there. It's possible that you might have to do maximum height or range or time, but it happens occasionally. It's usually for projectiles, it's going to be a component of a free response question. Usually that's how those are asked. Yay, kinematics down. We're booking it. All right, let's go on to our next one, which is Newton's laws and dynamics. You know the 3 Newton's laws. First law, inertia. I don't want to move unless you push me, okay? I call it the teenage law. So, tendency of an object to resist acceleration, resist any change in motion. I'm staying at rest unless you make me move. I'm staying in motion at a constant velocity unless you make me change, okay? Second law, that's our biggie, our F equals ma. And don't forget the units. Remember, it's a Newton. Remember what a Newton means. So it's a kilogram meter per second squared. Remember that. I know it's in your head, and you might say, why do I have to stop and think about it? Well, for a Newton, we oftentimes are doing Newtons times meters, or maybe Newtons divided by meters, and so on. So you need to be able to remember what is a Newton. So if you have to clean up the unit a little bit, you can, okay? Then, of course, our third law is action-reaction pairs. I know that's kind of saying it very quickly, but it's how those two objects are interacting. So as I push on the wall and the wall pushes back on me, an equal magnitude in amount, but opposite in direction, okay? There's oftentimes a mistake here on the test. What if I have something like a bird in my hand? The bird is pushing on my hand is pushing on the bird. But is the bird also then you think of it as how it's interacting with gravity as far as a weight? Not really. You're looking at it how it's relative to my hand. In other words, the objects have to be interacting with each other. You're not having it like skip something and go to another object. Just a quick reminder, F sub g is our weight or our force of gravity. Usually we assume that that's coming out of the center of mass or center of gravity of the object. Fn is usually how we write normal force. Remember, that's perpendicular. And that's going to be a push. So the push from the surface up onto, in a sense, the rear end or butt of an object. Could that normal force be at an angle? Yeah. When we're doing a car going around a racetrack that has a banked angle, we could. We could use the normal as at an angle if a block is sliding down a ramp. So it depends upon how your teacher taught you, whether you rotate the axes or you leave the normal coordinate plane and you do the component of it. Either way is fine. Either way, when we're grading the AP test, we understand. Okay, so we can do those problems. Applied force is usually the thing that's pushing. They usually say a force is pushing on this. We call that applied. Tension is F sub T, or tension is just T. And that's usually a rope, a string, a chain, a wire, and that's always a pull, never a push. And then friction, of course, is F sub F. A lot of times on the C test, they don't write it that way. They just write it as a fancy F, and it's okay either way. And remember, friction's always going to be parallel to the surface. So let's say it's something like a picture frame on the wall. Friction's going to be along the wall, up and down, or side to side. So friction could be vertical, friction could be horizontal, or friction could be at an angle. It's kind of independent based on the surface itself. And realize the friction's going to be independent of whatever a force you're applying. Now for friction, we've got static and kinetic. Who's bigger? Static, stay, S and S, okay? Static, stay. It takes more energy for me and more of a push to break me free from that surface. So static is going to be larger. And you've got your general formula there for friction. And like I said, oftentimes they'll kind of abbreviate it or put it with the kind of fancy F on the equation sheet or in questions. Now, most likely you did something with drag or air resistance in your class. You probably dropped something off the second floor or so, and you were able to calculate it. There were two main equations you had, one for the small objects and slow speeds, and then one that was kind of a general case. Do we have a likelihood of getting a question like this? It does happen from time to time, but it's not like universally every exam. It's more asking you how drag and resistive forces are acting instead of you always calculating it. So if it's something that you've done in lab, please, by all means, go over it one more time. If it's something you haven't done in lab, study something else because it's not such a huge component that you're going to have to reteach yourself tonight. It's not worth your time in that case. Free body diagrams, I do want to just draw this. I'm sorry, I can't help myself. So free body diagrams, if you have a dot, please make sure your arrow is on the dot right here. It's touching. Your arrow or ray is pointing in the direction you want it to be, and you want it to be as proportional as possible. If they give you some sort of graph paper behind that dot, you need to draw it proportionally. If it's something like this, where you have a ramp, yes, I draw so beautifully. And here's a wheel. If it's a force diagram instead, we're usually drawing the forces where the forces are applying. So for example, here, we're going to have our weight coming out of the center, okay? But our normal force is going to be coming off the surface, isn't it? Because it's coming from the surface pushing on it. And our friction would be along the surface, where you might have drawn that same diagram as a free body diagram with friction going this way, normal going this way, and gravitation going this way. Now, if I don't label it, am I going to get my full credit? Probably not. If I draw extra parts on there, am I going to get my full credit? Probably not. If I draw extra things, will I get it? Like say I put the components. No. So this is the one place with free body diagrams and force diagrams that you kind of need to be careful and do exactly what they're saying. And they're probably the easiest points on the test, but you need to follow the directions and read that carefully as far as what they're asking you for. Okay. And yes, my beautiful drawing abilities. Translational equilibrium, that's when that net force is going to total to be zero. So in other words, kind of like your tug of war. If I'm sitting on the chair, the normal force is equal to my weight. I'm not breaking the chair. But what if I was sitting on this chair on the Tower of Terror at Disney, and all of a sudden the floor is dropping. Well, probably I lift off the chair, don't I? So at that point, are the sum of the forces zero? No, I'm accelerating. So is the chair. Okay. So you need to kind of pay attention to when that system's in equilibrium, when everything's equaling each other, and when that system is accelerating as well. Let me erase real quick. There we go. Okay, check. We did that one. How about 3? Work, energy, and power. Remember, work and energy are both scalar quantities, so they do not have a direction. They only have a magnitude. And remember, our general formula for work was work is FD cosine theta. That cosine of theta is only there because we're looking for the force and the direction, the force and the displacement to be going along the same direction. Now, with that equation, you're truly looking at just a constant force, okay? Constant push is being given. However, we have our second one where we're looking at it as the integration of it when we're looking at it as a non-constant force. So that force is variable as it's being applied, okay? So you know when to use which, constant force or variable force, okay? Now, you also in this section had a neutral object, a stable object, and an unstable object. A neutral object would be something like, I played baseball, so a baseball rolling along a table. That would be a neutral object, that the potential energy is staying constant no matter how this object rolls. A stable object, I almost knocked over my coffee this morning. Think about that. So as the coffee cup started to tilt, it wanted to come back. That's going to be my stable object. So as the object wants to come back to its original position, that's going to be a stable object. An unstable object is one where as you tip it, it just completely falls over. So I like to think of this one as an ice cream cone. So if you've got the ice cream cone balancing on its tip and you barely got it balanced, and as soon as you blow on it, that ice cream cone falls over. So that's going to be an unstable system. Okay. In this section as well, conservation of mechanical energy. Remember, there's 3 conservation laws: matter from chemistry, energy, and momentum. So we've got 2 of them, okay? We've got energy and momentum. So conservation of mechanical energy is just saying, in a nutshell, what I start with is what I end with, okay? We could have kinetic, like our first equation, potential gravitation, like our second equation, or if your teacher prefers elastic or spring, for our third equation. It just kind of depends on which way. I like to put right here for the x. I like to say that this x is not just x, it's our change of x. And I really prefer that because remember, for this x value, it's not what the spring is as it's sitting there in your hand. It's how much you stretched it or how much you compressed it. That's what this x actually is. And so I oftentimes, even though that's not the general way of writing it, I'll put a change of x in here just to remind myself, particularly when I'm nervous. Okay. Here for our work kinetic energy theorem, all we're saying is work is kinetic energy, and we're connecting the ideas. For some reason, this one tends to be difficult for students. I'm not exactly sure why, because it's just plugging and chugging, but remember what it is, okay? And if this was variable for work, we could change this side of the equation if we needed to, okay? Now, since we said energy can't be created or destroyed, what does that mean relative to these big, huge free response problems? Well, if the system itself is isolated, what does that mean? That means the things that you're looking at are acting and nothing is acting from the outside. There's nothing external acting on your system. If there's nothing external acting on your system, then there's no energy going into or out of your system, okay? It's just what's there. What you start with is what you end with. So there's zero change in energy. Well, what if all of a sudden now in part C or double I say, now there's friction within your system, okay? That friction is probably going to be a conservative force or a non-conservative force. Think of what those 2 words mean. It's going to be a non-conservative force. So the pathway would matter. So that friction is going to create perhaps some sort of heat energy or some sort of internal energy to your system. So if we still say that energy is not created or destroyed, that mechanical energy is being shared with that internal energy from that friction. So in a sense, we're going to have some work that's what? Okay, it's non-conservative. So your teacher talked most likely about the path that the object takes, whether the path matters or the path does not matter. If the path matters of how you get there, then that's going to be non-conservative. If the path doesn't matter and everything is maintained, that's going to be conservative. Okay, so think of it in those parameters, and that should help you a little bit. One question I typically get is for circles, circular motion, is there work being done by the force? No. Because remember, as it's moving around the circle, the force, whatever it is, tension or weight or whatever, gravitation, is pulling you in. So the motion is going to be perpendicular to the force, and hence there's no work being done. And the last one in this section is power. And you've got the equation on your equation sheet, but also if you think in general terms of power is work over time, and then you can just manipulate it any which way you need to based on the equation. Check. We're getting there. All right, systems of particles. So technically at this point, you've hit half of the exam. Not bad. Do you think you could have gotten a couple little points here and there? Okay. Maybe a whole bunch of points here and there. So now we're just adding on to our score at this point, okay? Particles, and as far as linear momentum, you do have some center of mass questions from time to time. Often they're going to be something that's a multiple choice, where it'll be just like straight center of mass of where is the center of mass. But in free responses, you tend to have the object, or I should say the system, moving and having the velocity of the center of mass of the system. So if the two objects are originally together, and let's say the center of mass is directly in the middle, say they're equally shaped and equal mass, but then let's say this one shoots off, you're going to start to talk about that center of mass of that system as the two particles move apart from each other. You can also do the acceleration of that center of mass. Okay, and both of your equations are there. If you're noticing, they're very similar for the velocity and acceleration one relative to our position one. Momentum in general is our MV. I know you know, but we in C will connect that idea to our Newton's second law. And from that, when we're doing that derivative, we actually come up with a variation of that second law to include that changing velocity, okay? So we can actually manipulate it to get there. And I put the derivation there for you so that you can see it. What's impulse? The easiest way to think of impulse is car accident for me when I think of how much that airbag slows me down. So that is going to be that force and the time it takes that force is being applied. Now we can integrate that because usually we do get a graph for this one, and we're looking at that force versus time graph, and we're looking at that area that's underneath there. Now in C, we do abbreviate impulse as capital J. Sometimes in Physics 1, we don't do that. We just call impulse F times T. So depending on which way you learned it, if you did take Physics 1 or if you're now and C, you may do it either way because the readers do know. Now, elastic versus inelastic collisions. What does that mean? Elastic means I'm bouncing off, okay? I'm not stuck at any time. Inelastic, I can stick, or the objects can get deformed, or there can be some sort of sound you hear, or maybe some heat that's lost. So in something that just bounces off, my momentum is conserved and my kinetic energy is conserved. But in inelastic, if I stick, or if I get deformed or sound or heat, I'm going to lose kinetic energy. On those two ideas, That's usually a part A, a part B, the I, a double I, where they're having you do the pieces. So how do I know if I'm the person doing the problem? They've oftentimes asked, is this a elastic or an inelastic collision? How do you think I can figure it out? I'm going to look at the kinetic energies, the before and the after. If my kinetic energies match, yay, I'm elastic. If my kinetic energies don't match, I'm going to be inelastic. So that's the easiest kind of test you can do. Check. We're making it. Okay. Rotation to me is a huge subject. I'm surprised that they give us such a small amount. Well, it's not a small amount, but it's so much that can be put into this section. There's rotational kinematics and rotational dynamics. Now, the kinematics, I love them because you're just basically taking your linear kinematics and now putting the things in a circle. So you're going to have your displacement going from x to theta. You're going to have your velocity going from v to omega. Okay, so these things are kind of consistent. Acceleration goes from a to alpha. Now, with acceleration, you're going to have a centripetal with pedal at the end, centripetal acceleration that's pointing in, and your normal angular acceleration is going to be that vector that is tangential. So they're going to be perpendicular to each other. Now, if you think about that, it's an acceleration. Should I have the amount, magnitude, or the direction, or both, possibly changing of my velocity? Yes. So kids get confused. If I'm going and maintaining a certain tangential velocity with a certain magnitude, how can I be accelerating? I'm accelerating because my direction is constantly changing as I'm motioning around that circle. Okay. And here is your big translational to rotational transformations. So if you think of X or S is R theta, V is R omega, and A is R alpha. I think the only one they're giving you on the equation sheet these days is the top one. But if you can think of the top one, the other ones kind of flow directly for you. So you can make any of your kinematic equations change into angular kinematic equations very easily. So you could just write it out and then transform it. As far as the period, I've written it there as well. Think about when you're thinking about a circle, how as you move around the circle, you're moving around that circumference. And if I go around a circle for a circumference, I've gone 2 pi radians or 2 pi r around that circle. So if I do that in a certain amount of time, I'm getting my linear velocity. Now, speaking of centripetal force, remember, and people get messed up on this on the test, centripetal force isn't its own entity. It's not like its own special F sub T or F sub G. Remember, you never label it on a free body diagram. That's a sure way to lose a point, okay? Sure way to lose it. That would be considered an extraneous force. Centripetal force is really a mass times acceleration. And it's usually due to somebody. So it's due to friction, it's due to tension, it's due to gravitation, it's due to normal force. So you can put that MA of centripetal equal to any one of these. And remember, centripetal is in. So it's pointing towards the inside of the circle. So since it's pointing in, we count in as positive and something that moves me out as negative. So again, centripetal means center seeking. Your equations are both there on your equation sheet, not a biggie. And remember, we're going to then equate this, let's say, to tension, or equate this to a component of normal, or a component of weight, or gravitation, whatever it is. So it's not its own entity, it's a mass times an acceleration. And as I mentioned earlier, for our centripetal, or our overall acceleration, our centripetal acceleration is going to be inward, and our tangential acceleration is going to be tangent to the curve. So we can find our overall acceleration as our just straight Pythagorean between the two. I know I'm speaking fast. I'm trying to make sure I get everything in for you. Okay. That was the kinematic part. Now let's think the dynamic part, okay? When we start to think of dynamics, what are we doing? We're going from linear to angular. So now my mass is going to change into an inertia. So we have a various inertias of various objects that we have. Now, if we have a more complicated system, like say a wrench, a baseball bat, something of that nature that's not a point or a regular object, we're going to use our parallel axis theorem so that we can, in a sense, take that spread out object and come up with the inertia for it. However, most of the time, we're going to use just straight inertia. And the most common ones on our exam for C is going to be a particle or a point. And that's going to be the same inertia as a hoop, which is just our mr squared. A cylinder, same mr squared, but we put that coefficient of a half in front. A rod, about its middle, so 1/12, or a sphere, something like, say, a baseball that has mass on the inside. So these are our most common ones. Now, are they going to make me memorize them? The answer is really no. They usually give them to you. But there's no harm in just looking at them one more time before you go to sleep so that you can remember. Everybody's got an mr squared in there, and it's just a matter of, do I put a coefficient in front? Okay. Torque is also part of our dynamics. So if we thought about it, F equals ma, we're going to eventually move that to F, or torque, is equal to inertia times alpha. So we've moved it into our angular terms. We can, of course, do the derivative of that, and we can get our derivative of our angular momentum. We also have our torque here with F times L, or perhaps your teacher had called it F times R for radius. Lever arm is L, which means, again, the radius to the pivot point. It's either way, but that's our angular transformations. We can angularly transform our kinetic energy as well, and our momentum. For our momentum, it varies depending upon what the question's asking. Sometimes it's just asking you the I omega, so you're just doing like a straight linear momentum, but sometimes there's more complicated things going on there as far as your angular momentum, and you'll choose the second one. I believe both are on your equation sheet. Now think in terms of this though. If the torque stays the same, so think about that. If the torque stays the same, most likely the force in the lever arm are staying the same. And if those items are staying the same, most likely your momentum is going to be maintained as well. Okay. There was a question we were going over in class the other day about that. That's why I remembered to mention it. Okay, how am I on time? I'm doing good. Okay, 5. And now my 2 small units. All right, simple harmonic motion or oscillations. So that's going to be my periodic motion going back and forth over the same path. Most likely, you're going to be a spring and a mass on a block. However, they do give you pendulums as well from time to time, but much more frequently, proportionally, are going to be masses on springs. If I move something over to its maximum location, that's going to be my amplitude. So if I completely compress the spring, that's going to be my negative amplitude, or completely stretch the spring, that's going to be my maximum amplitude. So we look at those maximums and minimums for our potential energy. Remember, at those 2 locations of maximum, that's where my force that's restoring is going to be the largest. I want to come back to equilibrium. At those 2 amplitudes, maximum and minimum, that's also going to be where my acceleration is at a maximum. Whereas at equilibrium in the middle, that's when my velocity is going to be the maximum, and my force to get back is going to be my minimum. Again, for our pendulum as well as our mass on the spring, both equations are straight there on your equation sheet. And if you're given something of that nature, it's going to be a plug 'em, chug 'em type of thing. And you're going to be like, yes. When you look at Hooke's law, remember Hooke's law, you probably did one where you had a spring and you were hanging different masses on it, or maybe you did it horizontally with a spring in lab. Hooke's law is basically the force is equal to negative kx. And we oftentimes are not doing it exclusively by itself. We're trying to come up with the acceleration of that block. So when we manipulate that equation, we're going to get that our A is going to be negative km over x. And usually we pull it to our maximum amplitude or squish it to our minimum amplitude. And if you can kind of think of Hooke's law and derive from there, because this is something that's frequently done on the test, we think of acceleration and we think of velocity and we put those two derivatives with it, we can come up with our equation for Hooke's law relative to it. Can you kind of see where I've done the math to show you? So that's not given straight away on your equation sheet, but it's not that hard of a manipulation that you could do that in terms of part A, part B, part C, okay, on your exam. Now, period by definition is going to be the time it takes to do one cycle. Okay, so to go back and forth once. Frequency is the inverse of that. So it's going to be how many cycles I do in a second. So we have frequency and period with this straight spring or with the pendulum. But we also can connect that idea of a mass on a spring or a pendulum to an angular frequency. And for angular frequency, you've used omega, and that connecting equation for you is going to be the 2 pi frequency. And I believe that one's on your equation sheet. And so we can connect that idea with what we derived on the last page, and we can come up with our final equation. Okay, so this is how we're going to get at that A cosine omega t and all of those that are given on the equation sheet. This is that derivation that they're wanting to see. Check on number 6. I might be a couple minutes over, I'm sorry. The last unit is gravitation, and gravitational force, remember, is Newton's universal law of gravitation. Nothing funky doodles about it. It's just the straight G for our constant, mass 1, mass 2 over r squared. Couple of tricks of the trade. That radius in the denominator, they do like to trick you, okay? Remember, if it's something in orbit, space shuttle, ISS, whatever, you're going to do the radius of the planet plus the altitude of how high that object is, and that entire quantity is what's going in the denominator. Most likely, that altitude is going to have a very minimal effect, but it can have an effect depending on what they're doing. So be sure you're adding it in there. That big G is one of the couple things that are on that constant sheet that we'll actually use. So don't memorize it. It's right there for you. And don't forget its nice little complicated chunky unit that it has. Now, 2 views, okay? If I'm looking at it from the surface of the Earth, so we all are right now, we're going to say our weight is going to be our mass times gravity. We're on the surface of the Earth. And we can equate that to Newton's universal law of gravitation. And when we move things around, we end up solving for our gravity. And this is how we get our 9.8 or 10, if you prefer, meters per second squared. So we use the mass of the Earth, the radius, and where we basically are. Our altitude right now would be 0. I'm in Florida, so it's 0. Now, that's how we get our fairly constant number of 9.8 meters per second squared. Well, what if I'm in Colorado on the top of Pikes Peak? I'm a little bit further away, aren't I? So I would add in that altitude, and perhaps my gravity would be just a tad bit less. But even if I'm at the very bottom of the ocean or on the tippity top of the Himalayas, I'm not going to have a gravity that's all of a sudden 15, okay? Or a gravity that's all of a sudden 5. We're pretty much consistent as long as we're on the surface of the Earth. So hence, when we're doing potential energy, we've got our mass, our pretty consistent gravity times our height. So this is pretty much when we're at the surface or close to it. Well, what if I'm viewing not from the surface of the Earth? Okay, maybe I'm all the way out there at Mars, or maybe I'm at Pluto, or maybe wherever. So I'm not viewing from the surface of the Earth. Then we're not going to have the acceleration due to gravity as some constant, because we're going to have this really weird R between us. That's when you tend to use that other equation that you have right there on the bottom of your equation sheet. Where instead of potential energy giving us mgh, we're now going to have those components of our big G, the mass of whatever object it is, again, say the space shuttle, the mass of the Earth or whatever planet you're talking about, and the singular radius underneath. So that's when you change over to that secondary equation. Okay. Also, if you do think of the Earth, I wanted to point, oops, sorry, I went backwards instead of forwards. I meant to go here. There's two things of Kepler's law that we typically have to find. This is one of them with the velocity, and that's usually our escape velocity. And the second one is our period. And I just want to hit them real quick. Remember, centripetal force is not its own entity. We're going to equate it to something. And here I equated it to gravitation. When I clean that up, I'm going to get that escape velocity, okay? This is how Kepler came up with these equations. This is how we did his third equation, okay? If we look at that same velocity and we put in our circumference over time, so in a sense, our displacement in a circle over time for that velocity, we can solve for the period. Those are two derivations. They are not on your equation sheet. They have been asked a number of times recently. And so I'm bringing them up because they have been asked in a more frequent sense. So those derivations, again, you may have to do. Check, we did it. How am I? Yeah, I finished with 2 minutes to spare, or 2 minutes over, not too bad. So good luck, my dears. Please, if I went too fast, slow down the video, look at it again. I tried to give you a bunch of just little quick ones to remember or to refer back to right before the exam. You know more than you think you do. Remember, you have to think. It's not memorization. Look at the question, read it a second time, think about the physics behind it, and then answer, okay? Jot yourself little notes on the side so you can keep track of what you're doing and answer everything. If it's a multiple choice, put that same answer repetitively. If you don't know, but if you can eliminate things, make sure you do, but answer as much as you can. The exam is not terribly long this year, so you're going to be just fine and get every little point that you can from everywhere you want, okay? So good luck to you. Get some good sleep. Don't forget to eat, okay? And I hope that you all score beautifully for tomorrow.
Great. And Mrs. Ruiz-Houston, thank you so much for this review tonight. For everyone who's been watching, go ahead and press that like button, subscribe to our channel. We're so glad that you joined us here tonight. We're going to be going live for AP English Language in about an hour and some of our other physics subjects later this week. So just as Mrs. Ruiz-Houston said, good luck. Trust yourselves tomorrow. You're going to do great. Have a great night, everyone, and a great AP exam.